The theory commonly referred to as the Big Bang describes a period in cosmic history when the known universe was once incredibly dense and hot before expanding into the vast cosmos observed today. Some people see the Big Bang not as a conventional explosion, but as the rapid expansion of space-time from an initial condition. Over the last century, scientific observations such as cosmic expansion and the faint glow of the cosmic microwave background have strengthened confidence in the Big Bang model. Yet, one of the most compelling mysteries remains: what, if anything, came before it? Current frameworks allow us to peer back only so far before our mathematical equations stop offering meaningful answers. That boundary prompts a fundamental question. Did the Big Bang emerge from an earlier configuration, or is it in fact the ultimate starting point of everything? In examining how the universe began, many rely on the idea that general relativity merges space and time into a single entity called space-time. At the extremely high densities and temperatures of the early universe, classical physics breaks down, implying that new insights will likely come from a more advanced theory. Still, some researchers have proposed scenarios for what might lie beyond the Big Bang. Their proposals, though speculative, attempt to reconcile what we do know with the possibility that there was more going on than a simple birth event at time zero. Some theoretical cosmologists speak of a so-called cyclic or bouncing universe, in which the universe repeatedly goes through expansions and contractions. Over immense stretches of time, everything might collapse into a singular state and then rebound in something akin to a new Big Bang. In that view, time may extend indefinitely into both the past and the future, with each bounce erasing many remnants of what came before. Such a story suggests that our present cosmos is simply the latest cycle in a grand recurring sequence. However, modern astronomical data, indicating that cosmic expansion appears to be accelerating, complicates that picture. The presence of an unexplained force labeled dark energy is driving galaxies away from each other faster and faster. If this accelerated expansion continues indefinitely, it becomes difficult to imagine how a collapse and subsequent bounce could ever occur. On the other hand, if future discoveries point to alternative cosmic evolutions that allow a slow reversal under certain conditions not yet fully understood, the idea of a cyclic cosmos might return to the table. Another perspective focuses on an inflating multiverse, where the Big Bang of our region is treated as one bubble in a much larger reality. This concept gained traction through inflationary cosmology, the notion that just after the Big Bang, the universe underwent a burst of extremely rapid expansion. The impetus for this exponential growth is attributed to a high-energy field. Although that inflation ended in our observable cosmos, some propose that inflation continues forever in other, distant expanses. Through random quantum fluctuations, different bubble universes might stop inflating at different moments. One bubble may possess physical laws or fundamental constants different from another bubble. Our observable region is merely one bubble among a near infinite sprawl of universes, each with its unique trajectory. If so, the question, what came before the Big Bang, might be answered by saying that we emerged from a pre-existing inflationary field. Our local Big Bang could be a patch of space that cooled down and formed galaxies, while beyond that boundary, inflation keeps going. This concept is sometimes called eternal inflation. Though it offers an extraordinary vision of reality's scale, it is supported more by theoretical reasoning than by direct observation, leaving many open questions about how or whether such a cosmic tapestry truly exists. A third proposal is that our entire universe may have emerged spontaneously from nothing, where nothing is defined in a manner consistent with quantum theory. Quantum physics allows for fluctuations to appear and vanish on very short timescales without violating conservation laws, so long as these fluctuations balance out their net energy. Some theorists propose that if fluctuations can occur for tiny bits of virtual matter, then under certain conditions, a whole space-time bubble might pop into being. If that bubble inflates quickly enough, it could become a full-fledged universe. Moreover, if the net energy of a closed universe is zero, with positive energy from matter counterbalanced by negative energy from gravity, such a creation event might be feasible in principle. This is an unsettling suggestion for those who envision nothing as an absolute void. According to some quantum views, Even nothingness can contain fundamental laws that permit ephemeral bursts of existence. Although these models differ, they share a theme. The Big Bang might not be the first or only event of its type. Rather than the cosmic origin being a single uncaused phenomenon, it might be part of a larger pattern or a natural quantum occurrence. In each scenario, crucial questions surface. For the bouncing universe approach, we must explain how advanced expansions can reverse direction. For the inflationary multiverse, we wonder why inflation stops in some regions and not in others, and whether such an infinite froth of universes is truly meaningful if they cannot be observed. For the universe from nothing argument, we ask why quantum laws themselves exist, or how to conceive of a reality prior to any definable space or time. Each idea attempts to an understanding of cosmic origins beyond the limits of current physics. There is also the challenge that any talk of before the Big Bang might be rooted in a misunderstanding, since time as we measure it may have arisen only at the moment of the Big Bang. In other words, if time is not a constant backdrop but a dynamic component of space-time, the notion of before could lose its normal meaning. Some people have compared this predicament to asking what lies north of the North Pole. By definition, once you reach the North Pole, there's no further north to go. Some physicists believe the Big Bang might be a comparable boundary for time. Nevertheless, curiosity drives speculation. Humans naturally try to understand how and why the cosmos came about. Observational breakthroughs, like careful measurements of the cosmic microwave background, have revealed clues about the earliest phases of cosmic history, but those glimpses stop short of telling us about anything prior. The singularity that emerges in certain mathematical models is a sign that present equations are incomplete under those conditions. To unify Einstein's curved spacetime with quantum mechanics likely requires a deeper theoretical framework that can handle extreme densities and energies. Such a union might reveal not only the fate of cosmic expansion, but also the puzzle of the Big Bang's origin. Meanwhile, the standard model in cosmology, sometimes labeled lambda CDM, has its own open issues. It introduces concepts like dark energy and dark matter to explain observed phenomena, yet their fundamental nature remains elusive. The name dark largely means we don't know what these phenomena truly are. Although the model elegantly describes many aspects of cosmic evolution, the possibility that it might be incomplete or in need of major revisions remains alive. If new evidence or unexpected discoveries arise, they could force us to re-envision not just the future of cosmic expansion, but its earliest beginnings as well. Some people wonder if advanced telescopes or gravitational wave observatories might soon reveal data that clarifies these enigmas. Projects scanning the cosmos for subtle signs of primordial gravitational waves hope to find direct imprints from the inflationary era, if it indeed occurred. Although the detection of such waves would not by itself solve the question of what came before, it might confirm an essential piece of the cosmic puzzle, lending more credibility to inflation-based multiverse theories. Conversely, a lack of evidence could invite alternative lines of thought, maybe new approaches in mathematics or breakthroughs in laboratory physics that help conceptualize times prior to the Big Bang. In daily life, these questions might seem distant from practical concerns, but they tap into a shared human fascination with origins. The story of how everything came to be, space, time, galaxies, stars, and planets, resonates across cultures. Historical records show that numerous mythologies and philosophical systems have attempted to address the notion of cosmic birth. Modern science brings high-precision measurements and mathematical rigor to the conversation, but the sense of awe remains. Whether the universe repeats cycles, emerges from quantum fluctuations, or belongs to a vast ensemble of bubble universes, the scale and depth of the story are staggering. It's also worth noting that some lines of reasoning interpret the quest for a prior moment as potentially endless, because explaining a prior state might lead to an earlier one, and so on indefinitely. Each attempt to define an initial cause might spawn a further question. What caused that cause? The idea that cosmic history might have no absolute beginning at all might feel counterintuitive, but certain infinite or cyclical models remain on the table. Alternatively, one can argue that the concept of a cause does not apply to an event that lies outside conventional time. Each viewpoint reminds us of how incomplete our understanding remains. Thus, when asked what truly preceded the Big Bang, the most honest summary is that science has intriguing hypotheses but no definitive answer. The possibilities range from cyclical bounces to infinite inflation, to quantum spontaneous creation or something not yet imagined. Each scenario offers a separate window into how reality could be structured beyond the boundaries of our current observational horizon. Perhaps future experiments or a successful unification of gravity and quantum mechanics will help us see more clearly what happened at or before the Big Bang. Until then, these ideas serve as bridges between what we can observe and what we can only theorize. Our collective ignorance, rather than being a sign of failure, is an invitation to keep exploring, questioning, and pushing against the limits of knowledge. The very pursuit of understanding is part of what makes scientific inquiry a profound human adventure, reminding us that even the most settled of theories might be stepping stones to new revolutions just around the corner.